Taylor, speaking to you from locked down Melbourne. I'm from the Bureau of Meteorology here in Australia. Today I'm going to overview a perhaps novel concept for exploring the non-tidal forecasts available in the Bureau of Meteorology, with a focus on the representation of these models of along coast signals, and using an exploratory concept which I welcome your input on, where the different models are being reduced down to a waveguide path. And I hope this is a small step towards an ultimate goal of being able to provide what we might call seamless forecasting services across a range of timescales. With just a motivating, pragmatic example of why a public forecasting agency like the Bureau of Meteorology would care about non-tidal sea level signals. Starting point is that tide predictions, or harmonic tide predictions, which the Bureau also produce, are everywhere. They're used by coastal decision makers for all manner of purposes around the coast. They're a special type of forecast, very long forecast horizons. When the sea level deviates from these standard tide predictions, that won't be a surprise to people that that deviation occurs. It's especially to be expected when there's a local storm, or in the very extreme case, a tropical cyclone. But what I'm kind of say here is a sunny day surprise is we have many instances where tidal sea levels, or there's tidal anomalies, are driven by remote forcing or aren't due to local storms at all. And there seems to be any number of examples where this happens. In tidal anomaly on a sunny day may cause something which, nuisance flooding, we could call it nuisance flooding, or lead to a decision related to some piece of coastal infrastructure opening or closing. And so knowing about, or having better awareness or understanding our forecasting capabilities with forecasting remotely forced or propagating coastal signals is relevant to the Bureau of Meteorology, and arguably should be part of the forecast narrative, the story that gets told about forecasts by our forecasters. Now, the Bureau of Meteorology produces the tide predictions for Australia, but we also run a range of numerical or dynamic numerical models. In addition to our weather models, we have in operations today 3 different ocean models, each very different in their physical scales and physical representations, and designed for different purposes, but each of which at face value contain non-tidal sea level forecast information. Whether or not useful seamless forecasts can be derived from a heterogeneous model set like this is the question at hand. The models I'm going to talk about that are in operations today, and I'd like to stress that our range of models will surely change, continue to improve or evolve into the future. But what we have today for non-tidal sea level are 3 different ocean models, each with a free surface, each with different forcing. Here, model A, the relatively high resolution barotropic only 3-day forecast. What I'm calling B, 7-day forecast, data assimilating ocean circulation model, lag ensemble 7-day forecasts, and C, the seasonal forecast, coupled ocean atmosphere, multi-month forecasts. Heterogeneous models, I'd like to emphasize that the numerical models that we have, and I dare say we'll always have, none can do everything. And different models cover different time and length scales, each drawing the trade-off between forecast length and spatial and physical resolution and uncertainty sampling, drawing that trade-off at a different point for their different individual aims. But together they can span perhaps a useful forecasting window across these different time and scales. And when it comes to just illustrate that with a power spectral density plot of non-tidal sea level for a point in Melbourne, the different colours here are different model representations versus a processed observation. All of them have this nice red spectral general shape, but you can see quite a bit of deviation around at different special time and length scales. So no model's right, all models are wrong, but some are useful. The focus of this talk is a special interest in coastally propagating or coastally trapped signals, of sea level signals that is, and why would this be useful thing to think about. There's a special reason in Australia where we have a very large and long mainland coast. There's quite a long academic literature discussing the interesting properties of coastally trapped waves, free and forced coastally trapped signals, and as I mentioned in my motivating example at the start of the talk, there's practical forecasting reasons to draw forecaster attention to the existence of propagating signals along the coast. Here I'm illustrating perhaps the idealized coordinates that the literature on coastally trapped waves or coastally trapped signals has established, where in this idealized case we have an alongshore direction, an offshore direction. The coast is very long in the long coast direction, and we've got here an indication of the coast and a shelf dropping off to a deep ocean. How this could possibly be applied to the messy real coast and to perhaps apply it onto our let's call them messy realistic models is where I'm going to head with developing the waveguide path in the next slide. Now, taking our special interest in coastally trapped or coastally propagating sea level signals or sea level non-tidal sea level signals, and then thinking of this academic idealized coordinate system, how can we apply that to our heterogeneous models? What we've done here is first define an approximate waveguide path, and we're going to use this path once defined to subsample each of the models onto a common set of coordinates. Now, the path has been developed using a divide walk algorithm, where as if a set of dividers walked around the coast in the southern hemisphere direction, the dividers have a known length scale, and in this case they're proportional to the Rossby radius of deformation, a Rossby radius of deformation. So the actual length is slightly longer up here in the north than it is here down in the south, and the argument being that that's physically relevant to have that scaling. But the point for here is we've developed a path, this one-dimensional path, as it progresses around the coast at each intersection has what would be called locally offshore, so a direction of bearing which is offshore. It's not conformal, but it's offshore at each instance here locally. And to sample each of the models over here, where my pointer is now, if these were model grid points, the algorithm for sampling model progresses along this cross-shore profile until it finds the coastal point, so the model's own coastal point, and that is the point which is sampled into our waveguide coordinates. Now, importantly, this isn't a unique or best or only waveguide path. This is just one instance that's been developed here using a particular scaling, but importantly, we end up with a known length and a known scaling. So we're smoothing the coast effectively, and this smoothing has a known length scale. And following the Mandelbrot, how long is the coast idea? Should we change that length scale, the effective length of the path changes, and this comes to this concept of a fractilinear dimension. Not so important here, but point is, if you want to talk about how fast the signal propagate from this part of the coast to say this part of the coast, to do that properly, you would want to say how far has it travelled, and then we'd have to be able to put a length on that path, and that's part of the motivation here. So 3 different models, 3 different, very different forecast horizons, different data assimilating, not data assimilating. Point being, we can apply the same subsampling to reduce any model run onto this waveguide illustration here and compare that to tide gauge observation. What does it look like? This is where this is what it looks like. So on the left, we end up with these Hofmüller style diagrams. Well, it's one of the types of visualization that's possible. So here, this is the waveguide distance along the waveguide here, and then time in the vertical dimension. And just to progress through all these talks, let's point out that there are some signals, quite a lot of this diagonal striking, which could be, in some cases, free or forced propagating signals. And they're quite, maybe not unsurprisingly, they're quite prominent features when you view the model output in this sense. This one is this is model B, the oceanmaps forecast. And we can apply the same subsampling to other fields and other models. So in this case, it's a 3-day forecast from the barotropic surge model. For the same date, a 7-day forecast for the OceanMaps Barrow data assimilating ocean circulation model, and we can even go so far as to sample the wind stress falling in locally or path dependent along shore and cross shore directions. Now, I'm not going to go into discussing the analysing in great detail in a short talk. I'm going to flash past a few different visualizations to show what sort of analysis could actually be possible or has been done. So in this case, by subsampling both this is models A and B, short forecast and the 7-day forecast, we've just concatenated the first day of each forecast for a whole year of operational forecasts, or forecasts using exactly the same forcing, mind you. And then I can difference them in the coastal waveguide coordinates. And there's, again, quite a lot of this diagonal striping, which is indicative of the idea that the models, it's no surprise that models are representing the non-tidal sea level differently, but it's informative to notice that some of those differences are quite prominently have this coastal directionality to them. We do the same process for observation. So here, unfortunately, I don't have a lot of tide gauges on the west part of what available for this study, but each of these stripes corresponds to a tide gauge. And here I've taken a difference between model B, ocean maps, and or processed observation. So these are adjusted sea level residuals. And again, we're seeing the fact we're seeing some sort of diagonal striping here perhaps is indicative of either poor or underrepresentation or something going with representation of non-tidal signal which has this coastal pattern to it. Boiling down these tide gauge versus model comparisons that can be produced using the waveguide projection, we can end up with a skill metric in a spatially ordered layout here. So this is distance on the waveguide, so from up on the northwest shelf right round to the east coast. In this metric, lower is better, so lower score is better, and we're seeing the higher resolution model performing better for most of the coast, which is great. But it's very interesting to notice that they invert here. Won't go into that now, but that might have something to do with the baroclinicity of the longer model. Now, as a very first look at the seasonal forecast here, we're just in a very hand-wavy way saying, look, you can apply it to the seasonal model as well. And here we've overlaid a whole year of forecasts, and this red cloud here for these two locations is from the seasonal forecasting system. So wrapping it up, one of the messages here is that seamless coastal sea level forecasting is worth pursuing, we think, on the strategic plan. And for this little talk here today, we've talked about waveguide projection, which is a novel subsampling approach where we're producing ordered or physically ordered grid-independent coastal subsets from the models, which lets special focus on the propagation properties or apparently propagating properties, and may even be useful for visualizations that could influence forecast their information into the future. So I'll invite your critical input and stop there.